So hello everyone, welcome to Modern Semiconductor Devices for Integrated Circuits lecture number 16. I think last time we have derived the equation for the potential, the electric field and the depletion region width. So today we are going to solve the numerical. So write down numerical on the topic will be numerical on PN junction under zero applied bias. Under zero applied bias. Alright. So let's write down a numerical statement. Number one, an abrupt and uniformly doped PN junction has doping levels Na equal to 10 raised to 16 per centimeter cube and Nd equal to 10 raised to 15 per centimeter cube at 300 Kelvin. Given intrinsic carrier concentration Ni is equal to 1.5 into 10 raised to 10 per centimeter cube and epsilon of silicon, epsilon s, will be equal to epsilon naught into permittivity of silicon. So permittivity of silicon is given as 11.7 and epsilon naught is 8.854 into 10 raised to minus 14. Alright. So we need to find first built-in potential, next space charge width, third peak electric field. Okay. So this is the numerical statement. Completed. So let's start. So what is built-in potential denoted as VPI, space charge width is W, and maximum or peak electric field is EM. Okay, so write down first for an abrupt PN junction, VBI. What is the formula given by KT by Q natural log of NAND upon NI square. Alright. So what is KT by Q? Yeah. So KT by Q is 26 millivolt at T equal to 300 Kelvin. Okay. So substitute the values over here. 26 into 10 raised to minus 3 into natural log of Na is 10 raised to 16, Nd is 10 raised to 15, and Ni square is 1.5 into 10 raised to 10 the whole square. So VBI will be 26 millivolt. You can solve this in a calculator. This will be 10 is to 16 plus 15 minus 20, and down will be 2.25. So let me know the value of VBI. 63. Yeah, that's right. So this is my built-in potential. This is VBI. Okay. Next, we have to find out the space charge width. And VBI is always in the range of 0.6 to 0.8. Completed this? Use your calculators. Don't just directly write down the answer. Next, I'll write a formula for space charge width W. W is given by under root of twice epsilon s upon q into VBI multiplied by Na plus Nd upon Na Nd. Okay. So in the first step, you got the value of VBI. So if VBI is incorrect, W also will be incorrect. So now calculate this. W is, first of all, epsilon s. How much is epsilon s? Epsilon naught into epsilon silicon. So this is 8.854 into 10 is to minus 14 into 11.7. Calculate this. How much is this? 8.854 into 10 is to minus 14 into 11.7. 1 point. So it will be 10 is to minus 12, right? So this we can approximate ki it is 10 is to minus 12 only. So we substitute that exactly over here. So 2 into 10 is to minus 12 into 0.637 divided by 1.6 into 10 is to minus 19. Now calculate this also and keep it ready. What is Na plus Nd upon Na Nd? Acha, you can put it inside and calculate directly also, no problem. So this will be multiplied by 10 raised to 16 plus 10 raised to 15 divided by 10 raised to 16 into 10 raised to 15. See to it that the calculation should be proper here. So let me know whatever answer you will get in centimeters. Then later on you can convert into micrometers. It's okay. How much it is? No. It's around 0.93 into 10 is to minus 4. Width is small. The answer is 0.93 into 10 is to minus 4. Please check. So it will be 0.934 micrometer. So this will be the space charge width. You have to be very careful with your calculations. That's what I've written there. 934, 935, it's all fine. All right. Are you getting it? Same. Yeah. Third is peak electric field given by EM. Can you tell me what it is? Minus 2 VBI upon W. This is the formula. So minus 2 into 0.637 divided by 0.934 into 10 raised to minus 6. So calculate EM. Its unit is volt per centimeter. By default, unit of W is centimeter. By default, unit of EM is volt per centimeter. So what are you getting? 13.6 into 10 raised to 3. So actually we can write it as EM is equal to, anyone? Minus 13.6 kilovolt per centimeter. Normally your electric field is that much high also. Alright. So this is the peak electric field. Sometimes they will tell you to plot the PN junction and then plot the peak electric field, find out the W and all that also. So that's very easy to do. So how is the peak electric field? Don't draw it, just I'm drawing it for you all. This is the peak electric field. So this is EM. How much is W? This is W. Okay, so this will be X. This will be E of X versus X. How will you draw the potential? Potential how will you draw? Opposite of the electric field, na? ऐसे ना? So where will you show VBI? Over here. This is straight line, so this is VBI. So this plot is phi of X versus X. Why do we write E of X? Because it's a function of distance. Okay, they can tell you to draw this diagram or comment on the result also. So this is the way we can show them easily. Alright. Actually, it's a P plus N junction. Why? Because the doping of Na is greater compared to Nd. So it's a P plus N junction. Alright. Now let's check this out in NanoHub whether the values are matching or no. So I opened one terminal and kept. Let us check this out. We'll put the same values and check whether we are getting the similar answer or no. Alright. What was the material? Acha, here, how much was Na? 16, right? So here it will be 1. See, 10 is to 15 is here. So difference in concentration. Alright. N type and P type. So this is my doping versus distance. This will keep it same. Length we can keep it same. Both we can keep it at 6. What do you mean by number of nodes? See, it's written over there for better accuracy. Meshing. It's a meshing actually. So we can keep it 100. So we divide number of nodes Divide that 0 to 100 in a scale of 100, 0 to 10 in a scale of 100, ऐसे. Now material, what material we have selected? Silicon. You know, minority carrier lifetime is also there, I have taught you all. It's around, this is around 10 nanoseconds. So we can keep it as it is, no problem. Environment temperature is 300 degree Kelvin. Okay, applied, we have not applied any voltages, just wait. So let us check with this. So behind in the server, it's running and it will give you the answer in few seconds. See, this is the energy band diagram. All right, at equilibrium. Now we need to find electrostatic potential. Now, so this height should be how much? 0.654. Exactly, you got that? How much did you get? Up to 637. It's fine. Wait. Electrostatic potential at 9 nanometer. Yeah, we have changed some dimensions. That's why it's showing, but it's nearby. It's fine. Point. So what is this? This distance. As you can see, as I move around, this is the distance. Okay. Let us check the peak electric field. Here it is, right? How much it was? Yeah, you can see now here. It's 13.5 kilo. It's 13,000, right? So 13.6, 13.5, it's fine. Nearby, you are getting it. All right. So this is the way we can verify your answers. And how will you verify W? Net charge density. Distance between this and this point, right? W. Or how else we can find out? Yeah, that's the only way we can find out. So here, let me change the blue one. Blue one is the graded one. Understanding? So here, if I expand it, to calculate the distance from here, okay, to here, that will be W. So how much is the W? So here, if you can note down this value, this will be 6.95 micrometer minus, how much is this? 5.91. Around minus 5.1, and it's written that depletion approximation. How much it is now? 0.9 or 0.1? How much? नहीं माइक्रोमीटर करने की जरूरत नहीं है, just subtract the number. 6.95 minus 5.91. So it's fine. We are getting 0.9, right? So very close. You have put the other parameter length and all, it's different. So that's why it will make some calculation difference. But nearby we are getting the rough estimate. It's not that key, it's 0.9 micro and we are getting around something else. Same magnitude but slightly different is there. Alright. So this is the way we can verify your, actually you can see all the formulas which are intact. This is how you determine whether which type of junction we want, whether we want a P plus, this is a P plus N junction. You see what happened over here? On the, which is higher, Xn or Xp? Xn is little higher. So what does that mean? My N side is lightly doped. So depletion region is extended more over there. You can see there. Whereas depletion region on the P side is less. Why? Because it is heavily doped. On one side we have 1 crore, on other side we have 10 crore. So definitely the depletion region will be pushed that side. Alright. So now let's go to the next numerical. So write down numerical number 2. So first let us write the statement. Find the following for a silicon PN junction at 300 Kelvin for acceptor doping as 10 raised to 18 per centimeter cube and donor doping as 10 raised to 15. Comment on results obtained. Okay, what do we need to find? A. VBI. B. W. C. EM. D. XN and XP. Got it? Now you already know the formulas. Please start solving. Acha, what do you take if epsilon s is not given? We have calculated now how much it is coming, 10 raised to minus 12. Directly you use that. KT by Q, 26 millivolts. So these are some constants which you have to use directly. So let's start. So VBI will be KT by Q, natural log of Na ND upon Ni square. Actually, Ni square value also you should know. How much it is? Ni is 1.5 into 10 is to 10. No, normally we should remember them. If it is given, or else you have to know this. Yeah, 1.5, 1.45, it's fine. It is 10 is to 10. That is important. Okay. Ni is 1.5 into 10 is to 10. Ni square will be 2.25, right? So substitute it over here. So VBI will be 26 into 10 is to minus 3 into natural log of 10 raised to 18, 10 raised to 15 divided by 2.25 into 10 raised to 20. Now calculate this. So VBI will come out to be, so we are changing the doping from the last numerical. Na was 10 raised to 16, now it is 10 raised to 18. So definitely VBI will increase, but it will be in the range of 0.6 to 0.8. 0.757. So which type of junction it is? It is P plus plus N junction, right? What do you mean by P plus? Heavily doped. It is very heavily doped, but still we can write P plus N junction. Next is find W and EM. So let's do that. W is given by under root of 2 epsilon s by Q into VBI Na plus Nd upon Na Nd. So W is 2 into 10 raised to minus 12 into VBI is 0.757 divided by 1.6 into 10 raised to minus 19, and this will be 10 raised to 18 plus 10 raised to 15 divided by 10 raised to 15 into 10 raised to 18. So give me the value of W in centimeter or micrometer directly. Yeah, whatever value you get, that value is in centimeter. This will be again closer to 1 micrometer. Sorry. You have to be good with your calculators to solve this and get the correct answer. Yeah, what's the value? 9.7. 0.9 into 10 raised to minus 4. Correct? So that will be 0.97 micrometer. Okay. You understood now? If you convert this into meter, it will be 10 raised to minus 6. And a human hair strand is around 100 micrometer. This is 100 times smaller, the width of the PN junction. Next, what is EM? Minus 2 VBI upon W. Yeah, 15 point. Okay, that's all. That's correct. EM is around minus 15.6 watt. Kilovolt upon centimeter. That's correct. But we have to find XN and XP also, right? So let's do that. So next will be, do you know any formula? XN is NA upon NA plus ND into W, and XP is ND upon NA plus ND into W. This we have seen last time. So calculate it now. But why you want to? This is directly available, na? Directly you're finding xn. It's a fraction, right? As you can clearly see. So this will be 10 raised to 18 divided by 10 raised to 18 plus 10 raised to 15 into W, which is 0.97 into 10 raised to minus 4. So let me know how much is the answer. This will be 10 raised to 15 upon 10 raised to 15 into 0.97. See, ultimately xn plus xp will be W only. Alright? 0.96 micro, I mean, this now? Yeah, and this will be, sorry, 0.01, right? Why I said 0.01? Because if you add this to 0.01, you will get exactly. Check whether you're getting this or no. 9. Approximately same, no? So as you can see, P side is very, very heavily doped. So the extension of Xn is Xp is very, very small, whereas it's fully extended towards Xn only. Now, how do we comment on the result? So we can say that you have completed. So we can say that inferences. So let's draw that PN junction. What format? Just comment. This diagram I'm drawing just to explain you. So you're free to draw that also. This is XP and this much is XN. How much is this? 0.01, right? Micrometer. And this much is, this is 0.9. So what does it say? This is 10 raised to 18 per centimeter cube. This is 10 raised to total W is how much? 0.97. So this is W. Correct. So from the above we comment that your P region is very, very heavily doped. So P region is heavily doped and N region is lightly doped. So it's a P plus N junction. Correct? It's PN junction but P plus N junction. Second thing we can comment is Xn is very much larger compared to XP. What does that mean? That heavily doped region P plus, you can write heavily doped P side holds a smaller portion of depletion width. Correct? And so third we can say depletion region extension is larger on lightly doped side. Correct? Depletion region extension is larger, as you can say. This is also not a comparison, that is 0.1, this is 0.96, so it's very, very long. We don't have this much hypothetical junctions, but still. Now we have another topic which is a big derivation. I'll let you know what I'm going to discuss now next. And this is very, very important for all the remaining devices which are upcoming. This derivation will not be there in the ISC, but ESC you can expect. Again, for your ISC, there is no derivation from this subject also. Only numericals and concepts. I'll share you the questionnaire list, how can be asked, because it's your first time. So you're not aware of it. Okay? So, we have studied this characteristics, right? What is this characteristics? Diode characteristics, no? And what was the equation of this diode characteristics? ID was IS times exponential of VD upon VD ऐसे ही होता है ना something it's exponentially related to. So basically ID is a function of VD, or we can say ID is directly proportional to e raised to ED. So it's an exponential relation. So that means what, if you change the value of VD to a very small value, your ID increases to a very large value, as you can see, right? So here, let's say the value of VD is 0.6. Here ID is 1 milliampere. Now change it to very small value over here. So here your VD is 0.62, whereas ID has become 20 milliampere. So ID has increased by 20 times, whereas this has increased by 0.02 volt times. So that's the indication that it's an exponential relationship. So basically, this equation which we have written is incomplete. We don't know what is IS. We directly substitute. No? It's a reverse saturation current, but it's not. We have to derive the proper diode equation along with what is this IS and where it is coming from. Alright. So we have this is actually called as an ideal diode equation. This one, ideal diode equation. So let's write down. So this is what we'll do. It will take around one lecture time, but we'll start today. We have some time. At least we'll start with the approximations and all that. Prepare ourselves. Okay, understood? So we have to derive this equation in detail. What you know is this, right? But after this derivation is over, your reality will change. This is especially used when we design a diode. When we are working in a fabrication factory and we manufacture new devices. Not only PN junction. Actually, if you see, solar cell is also a PN junction only, but made up of different materials, not silicon. But the concept will remain the same. Okay, so let's start. Write down to derive. Next aim will be to derive and understand ideal diode equation. Okay, not only to derive but also to understand from the inferences what does that each and every term means. So what is the ideal diode equation? Anyone? It will tell you what the IV characteristics of the PN junction is, so that we will know how much current flows for a given amount of voltage. Okay, through the diode. So there are 3 steps of evaluation. So write down 3 steps for evaluation for further analysis. Step number 1 is we evaluate. This is from semiconductor physics. Evaluate diffusion flux for VA equal to 0. Acha, what is VA? Let's assume that across this diode, the applied voltage is VA. Externally applied voltage is VA. So this is VA. Are you getting it? Externally applied voltage. VA applied voltage is 0. So this is 0 bias condition. Next, evaluate diffusion flux for applied bias VA. Alright. Then next third one will be, in a PN junction current flow is due to diffusion only, right? So that's why we are calculating diffusion flux. Now third, combine diffusion with drift terms to get total current. Now you will say why drift arm is coming. Drift arm is coming only in the reverse bias. Because in a reverse bias, minority charge carriers comes into picture, and there is a small amount of current. That small amount of current is due to drift. So we'll at the end combine diffusion and drift terms to get the total current. All right? Yeah. Now we need to understand what will happen when we change, or what happens when the diffusion flux changes, and how does the variation of applied voltage affects it. So let's answer that question. Write down first. Diffusion flux variation diffusion flux variation with applied voltage VA. Okay. Now first let me draw the energy band diagram. For this we have to draw the energy band diagram. So how it is? I'm drawing it, okay, like this. Normally what happens? See here, these are same, right? This is my Fermi level. It is same throughout. Wait, plus first listen, and Eg is constant throughout the energy band gap. So this is EC, EV, this is EC, EV. Conduction band is nearing the Fermi level means what? It is a N region. And valence band near the Fermi level means it's a P-type semiconductor, P silicon. Okay. So this is the energy band diagram under. This is the energy band diagram under what? Equilibrium. And where is my VBI from here? This height. We cannot write VBI. We have to write Q into VBI. Built-in potential energy. Now what we are asking is, now we are applying the voltage. Externally applied voltage. So externally applied voltage, say what happens? We have a PN junction and we apply externally applied voltage VA, and VA is increasing. What will happen? This is your W. What will happen to W? So as VA increases, your depletion will decreases. So do you say more number of holes get diffused and more number of electrons get diffused? So the probability of diffusion increases. That means this barrier, which was earlier VBI, this will reduce. So the new formation will be, the new diagram will look like this. See this. See very carefully what I am drawing. Getting it? And over here, it will be down. This will be my new energy band diagram. So what has happened? This barrier which was VBI, which was preventing the carriers to flow, now it has become Q into VBI minus VA. Correct? The barrier is reduced now. Earlier it was how much? VBI. Now it has reduced by the applied voltage. And what is the difference between them? As you can see, it's moving away, right? So this difference over here is my amount of VA applied. E EV1 means what? Acha, you mean to say this? Actually, board shifts above. So if I draw it separately, wait, let me draw it separately over here. So this is what the energy band diagram looks like right now. So here, this one, EF, will be shifted over here. Both shifts actually, this EFN and this is EFP. Here it was same. Here EFP and EFN was same. Here it will shift. And why it is a shift? This is the amount of applied voltage applied VA. Are you getting it? Actually, both gets reduced. EC and EV both gets reduced. This is EV. Oh, this is EC, right? EC, EV. Are you getting it? Both get synced actually. And this reduced barrier compared to this is called as Q into VBI minus VA. Are you getting it now? So what has happened? I mean, here diffusion flux is proportional to, see there are number of carriers above also, right? Here there are number of carriers which are about to diffuse to the other side. So any carriers above the conduction energy level will be available for conduction. I mean, these carriers can go on that side and it will be available for conduction. Yes or no? Okay. So what happens is diffusion flux is proportional to the number of carriers having energies above EC. So these carriers can diffuse across this junction like this. So this is electron diffusion. Yes. Now the barrier is reduced. So do you have get more number of carriers? Now even the carriers over here are eligible. These carriers are eligible to diffuse, but they are not diffusing because बहुत ज़्यादा energy हो जाएगा ना. So these carriers diffuse from here to here. Now when the barriers has reduced, do you agree that more number of carriers are eligible to diffuse now on the other side? Hence the diffusion flux density increases. So that means how many electrons from the N side go to the P side is determined by how many electrons are having high enough energy to diffuse. And where does the energy they get from? The external applied bias. We have reduced the barrier. So earlier, let me say earlier, if an electron have to travel from here to here, it has to jump this much energy higher. It is much higher. Now it is at much reduced energy. Earlier, we have to jump from first floor to second floor only. I mean, from second floor to first floor, let's say. Now we have to jump from a mediocre level. That means, let's say, 1.5 floor to first floor. So easier, na, second way. Let's say third floor to first floor, and now it is second floor to first floor. So it's easier, right? So here it will be easier for the carriers to cross the junction because the high energy required is not required over here because the barrier potential is reduced. So earlier it was this much barrier. Now it has reduced. So it will be easier for electrons to go across the junction. All right. So that is the energy band diagram of PN junction under forward bias. This is the energy band diagram, PN junction under equilibrium. Just draw this and keep it. This is under forward bias, energy band diagram of PN junction.
So we'll be having IA on Friday.
Yes. Based on module number 1.
The entire module.
Huh. Yeah. You have noted down, so it's fine. So that's it for today.
So can you make the IA easier?